Lab 2, the motion of a falling object. In this lab, we set up two models based on different assumptions but the same fundamental principle, which yield different predictions, and compare them to the actual motion of the equivalent falling object and see which model yields which results. So, model 1 assumes the only force acting on the system is gravity, gravity being constant at mg, g being defined as 9.81, and if we apply Newton's second law, we should yield an acceleration of 9.81, or delta v over delta t of 9.81. Therefore, my prediction for this model is that we're going to see a linear velocity graph and a similar to a scalar multiple of an x squared parabola. To code this model was quite straightforward, since we can ignore the air resistance part of my code. All that was important was to set delta t to the frame rate, set m to the approximate mass of what I'm dropping, set g to our gravitational constant, and then apply Newton's second law as we see here, which I've already explained. Moving on to model 2, we are now adding drag, and as listed in the instructions, we are to assume that drag is equal to dv squared. Now this, using the same fundamental principle, yields a slightly different equation for acceleration. You can see the math here, where we have the same 9.81 but subtracted by dv squared divided by mass. Now, this is going to yield a very different graph for velocity against time, which will subsequently create a very different graph for position against time, as we will see when I move on to the graphs. But before I do this, I want to walk you through the code here. This 1.7 was yielded through testing drag numbers in the glow script and finding one that hugged the tracker line as close as I could get. It's obviously not exactly our drag coefficient, but it is as close as I could get it. And as you can see, the drag equation here is the same one listed in our parameters. Moving on to the tracker video setup, I decided to drop a piece of paper. Now, I explained this in the slide where I walk through my tracker, but I have an 18 centimeter yardstick, which I measured, the time interval equal to my frame rate. Well, that's not quite right. It's a 0.033 time interval. And the axis is set here to make the conversion to a spreadsheet more easy. Now, the tracker model against models 1 and 2. I think this is a very successful outcome. The air resistance model 2 is not perfect, and I'm going to chalk that up to 3 factors. 1, my B figure is not perfect. 2, the equation we're using for air resistance is not perfect. And 3, I have set my center of mass in tracker imperfectly. Or not perfectly. But as you can see, I mean, they're remarkably close, which was partly due to my testing, but they deviate in similar ways. Now, model 1, of course, starts out roughly the same, but as our velocity increases, just the lack of considering this air resistant throws it completely off track. Now, conclusions. Terminal velocity. Terminal velocity occurs when the net force of a falling object is 0, and therefore the velocity is constant. So the net force would be 0, making the change in velocity 0, making velocity constant. This can happen when there is a force to counteract gravity, i.e. air drag, and so therefore only model 2 can account for this because it's the only model that has another force to counteract gravity. Model 2 in my glow script predicted terminal velocity, but tracker did not yield terminal velocity. And I think what we have here is an imperfect equation for air resistance, and that's what's causing this. But as I said, model 2 is the only model that could predict terminal velocity because there's nothing in model 1 to stop gravity. Moving on to an object that's thrown downward. In my opinion, this would simply lead to a higher initial velocity, and this isn't going to change terminal velocity because the mass of the object is the same, its coefficient of air resistance is still the same, so the equation that produces terminal velocity is still the same. While the object's in free fall, the fact that we threw it earlier doesn't really change it. The only thing is that instead of working its way up to terminal velocity, it might have to work its way down to terminal velocity if we throw it hard enough. Here are some things I'd appreciate it if you considered about my video. I have ODS accommodations for dyslexia, and I have re-recorded this video several times. And ultimately, my condition makes it very hard to read from a script. And as regards background noise, I have tried to minimize it, so I'd appreciate it if you were generous in grading this video. Thank you so much for listening.